Hello everyone and welcome back to another Teach Astronomy stream. My name is Victoria, but you can call me Vicky, and I'm here with Professor Chris Impey. And we are going to be talking about Einstein's Monsters today. If you guys have been here for the last couple months, a little bit more than a couple months, we've been reading the book chapter by chapter every week, and Chris is here to talk to us about it as the author.
Okay, yeah, it's good to be here with you, Vicky, and looking forward to interacting with the audience too. Einstein's Monsters, a book about black holes, and I think it's my 8th book, which makes me tired just saying that, but was the most recent book I've written, and that was fun. Writing books hard, but you get into a subject and you just learn so much. I mean, I'm an astronomer, but I learned a lot of things about black holes I didn't know before I started writing the book.
Yeah. Yeah, so I have some questions prepped for Chris, but if you guys want to ask questions in the chat, feel free, and I'll include those as well. We'll kind of start with more stuff about the writing of the book, and then maybe we'll go into more of the science side later if people have specific questions on things that were covered. So first off, I just wanted to ask, what inspired you to do a book all about black holes?
A couple of things. The black holes are always of interest. They're exotic. Most people know about black holes, even if they don't really know what they are. And they're exciting to astronomers too, because we don't know everything there is to know about black holes. But a particular thing that motivated me was most people, and in fact, there have been a few books about black holes that really dwell on the black holes that are a result when a massive star dies. That's the first type of black hole to be discovered. But actually, in the last few decades, there's been enormous progress in finding and understanding these massive black holes that sit at the middle of all galaxies, actually. And my research in cosmology and my extragalactic research for decades has been looking at active galaxies like quasars, which are fueled by black holes, or trying to find black holes in galaxies that don't seem to be very special, but we know black holes are in all of them, so there's ways to look for them. So I've spent a lot of time as a researcher looking at massive black holes, and there was no book around that talked about the full spectrum of black holes, all kinds, including the possibility, for example, that there are tiny black holes as well. So I wanted to put it all into one book, which had not been written to this point.
Nice. Yeah, I like the way that you melded the history side of the original discoveries and the early observations with all of the science. And speaking of the science part, so like you said, this is your 8th book, and you do a really great job in both like these online sessions and also in your writing about making really difficult concepts approachable for those who aren't like astrophysicists like yourself. How I guess what is if there's something in this book, is there something that stands out as like a more difficult idea that you had to, or concept that you had to explain to the reader, kind of?
Yes. I mean, there are definitely some. I mean, the basics of black holes and event horizon, the region from which nothing can escape, that's not too difficult. People sort of understand that. Just how extreme the objects are physically, that's hard to convey, but you can use analogies. One thing that is very hard to explain, and researchers struggle with understanding it fully, is what's called the information paradox, the idea that there's a problem in the fact that everything that falls into a black hole can't get out. And so in a very general sense and in a physics sense, they trap information. Why is that a problem? It is a problem for physicists. So explaining that was actually quite challenging. And the other one, of course, which is also a high-level physics concept, is Hawking radiation, the idea from Stephen Hawking that black holes are not totally black, that they have a very low temperature, and therefore they emit radiation and also lose mass and are not eternal. So understanding Hawking radiation, which is a quantum effect, that is also quite challenging to describe and explain.
Yeah. As someone who is now in the sciences, kind of I didn't do the degree for it, but since working with the group, I've learned a lot more about astronomy and stuff. Really, it was a really good book to read because um, you don't gloss over the higher concept stuff, which is nice because I feel like either a lot of authors either write things very very simply and don't get into the more complicated things, or they go full out like this is an academic paper essentially.
Right.
um,
Yeah, it's good to find a middle ground, and it means sort of knowing who your audience is. I mean, you could write, yes, you can kind of write a very simple, trivializing almost book of Idiot's Guide to Black Holes, and that probably exists, I'm sure, uh, where you gloss over all the physics and of course don't have any of the math. I didn't have any math, but I was not neglecting the physics. And then you kind of throw the baby out with the bathwater. You lose the essence of the subject. This is very hard to talk about a technical field of science like black holes and not represent the physics reasonably well. So the middle ground means you're not using equations, you're not making people plow through a formalism, but you're not neglecting the fact that the physics is front and center in understanding black holes or in the things we don't understand yet. So challenging an audience is a good thing, I think. Yeah, you can shoot way over people's heads, and that doesn't really help you. It doesn't. It also reduces the number of people who might read your book. But it's usually a good idea to challenge an audience somewhat. As long as you don't sort of leave them in the dirt or behind or go way over their heads. And that's a hard thing to do. I mean, I run my writing by my wife, who's an artist, and she's taken science classes, so she knows enough. But she's a good example audience, or other people I know. And of course, the publishers run the book by people who are not astronomers when it's been written to make sure it's hitting the mark.
yeah. And so speaking of the writing process a little bit, what is the writing process like for a nonfiction science book?
Well, it's very methodical in a sense. I mean, writing a book is hard because it's huge. It's a 100,000 words typically, and you have to. Publishers now make you do a lot of the work. There's very little support in the publishing industry. You barely get editors working with you, so you have to pretty much write good prose and edit yourself, or get that right. You have to assemble your art program, the images, the figures. You have to get permissions for all those things. You have to keep track of them in a spreadsheet. You have to, if it's not technical writing, you tend to put all the technical stuff or back it up with papers in the literature, either in endnotes or footnotes. I tend to prefer endnotes because the footnotes kind of look ugly to me. And so the last few books I've had endnotes. And that just means you can just read through and not follow any of the endnotes and you don't miss anything important. But if you're the kind of person who says, well, I want to know more about that, or let's get into more detail, then you go to the endnotes, and that they will have references in the literature. And so in a book like this, there's 400 or 500 endnotes, and included in those are several hundred papers, references, research papers. And so you have to do all that. And so, that's a lot of work. It's just not just a matter of pounding out 100,000 words, which is hard enough for people who don't like writing. That sounds impossible. You have to just do it methodically. I mean, so blocking out time and knowing how to edit yourself and not having any writing blocks. You just have to write basically. But that's like most things. You can tie yourself up into knots anticipating something or wanting it to be perfect immediately when it really can't be. So so there's a set of disciplines associated with writing a book, and that's really the heart of it. It's a disciplined process.
Yeah, definitely. And speaking of those endnotes and stuff, when we were reading, it was so funny because I was flipping through at one point and I was like, oh, I think we have like 2 or 3 more chapters left, and then I got to the last chapter and I was like, oh no, that's all notes and like the index and stuff. But so clearly that took a lot of research time, even though you have done a lot of study in black holes and you know a lot of the information already. Just finding all those papers and being able to cite things and stuff. How long did it take you to research?
Yeah, I mean, the research is sort of folded into the writing, so I can't separate out how much time is spent research, but I'd say a lot. In the totality of the hours, however many thousands of hours, I don't like to think of a number, it takes to write a book. Probably half of it is the research, and and another, or maybe 40%, and another 10 or 20% is the figures and illustrations, and the index is done for you by someone. The publishers hire someone to do an index. That's a very specialized job, so not so
Gotcha.
easy for the author to do. So yeah, it's a good fraction of the time on the research because it has to be right. Even in a subject I know, I have to be sure I have the most current information. So I'm going to the literature and looking up stuff all the time.
Yeah.
And then I don't want to put ridiculously technical papers even in the end notes. So I have to pick the right paper if there's going to be a paper.
Mm-hmm.
Pick the right paper, and the endnotes can be more technical than the main writing, but not ridiculously. Again, so might even be some math in those, but not much. So writing good endnotes for the people who like a deeper dive, that's another sort of whole job actually, especially when in the end there's literally 400 or 500 endnotes in a book.
Yeah. And you mentioned like finding the papers to make sure you're up to date. I actually noticed when we were reading, some people were asking me like, "Oh, when was this written?" Because at the time when you had been writing it, we hadn't gotten the first picture of a black hole, and I thought that was just a crazy and very poignant example of like how fast things can move. Yeah.
And so that's the trouble with writing a science book in a field that moves fast, like astronomy, or biologist or geneticist would have exactly the same problem. Yeah, thing moves fast, and so I knew any astronomy book is in this situation actually. So I knew there would be things happening as the book was being processed, and it takes a year from submission of manuscript to the book coming out. In that year, almost certainly something important would happen. And you're allowed to make some edits when you're in production, so you do get one late chance to make some corrections and possibly add things. But at that point, the book is typeset essentially in a computer, of course, and it's flowing across pages that are all defined. So you can't add anything that changes the paging or the flow of the text more than a little tiny bit,
Mm-hmm.
or zero sum. You have to take out a sentence if you add a sentence. So it's a very rigid box you're in at that point. But
Yeah.
it does let you get a late breaking mention of a discovery, but that's all.
Mm-hmm.
And then, and then the next chance you actually get to make additions is if usually a hardcover has a run as a hardcover, and then they do a paperback, and the paperback can have changes. But again, it's basically the same book, so it's another opportunity for very modest changes,
Mm-hmm.
um, and you should have to wait till a second edition to make significant changes. So
Yeah.
you can't keep on the pulse of the research exactly with any book.
Gotcha. And let's see. Okay, so different subject a little bit. What was your favorite section to write, if there was a favorite section?
I did actually like writing the first chapter or two on the history of black holes because that some of that I really didn't know. I mean, as a researcher, I knew what black holes were, and I knew the derivations of Hawking radiation and all the properties of black holes from physics, and I knew what was going on with black holes that we've cataloged as dead star black holes or center of galaxy black holes, but I didn't really know the history. So that was interesting to find out, which is where the title of the book comes from, that Einstein really didn't believe that black holes were real physical phenomena. He didn't trust his theory, essentially. He thought they were artifacts. And many famous astrophysicists of the time, Arthur Eddington, probably the most famous theoretical astrophysicist in England, also didn't think black holes were real. So in the 20s and 30s, it was seen as an artifact of a very good theory, but seemingly implausible that it should exist in nature. So that was interesting. And then just the whole process by which the predictions of general relativity emerged over time, over decades. And then just the difficulty of finding the first black hole. 1969 was the first black hole, Cygnus X1, where the proof, the demonstration was really good enough that nobody had any doubt. But
Hmm.
that's a long time. It's decades after people theoretically thought not only the black holes could exist, but the theory of end of stars lives, those physics calculations by Oppenheimer, Beta, and others in the 30s and 40s said yes, these things not only could exist hypothetically and theoretically, but they probably should exist at the end of a massive star's life. So it's another 30 years before you detect the first one. So that's a long and difficult process by which you discover something that you've known might be around for over half a century.
Yeah. Yeah, it's a crazy, crazy journey, and that's yeah, the historical side of it, along with all the science and everything. But I thought it was really interesting. Um, so you mentioned it, the Einstein's Monsters title. Did that come from specifically just was it something that Einstein like the way he phrased something, or I think Einstein's Monsters is also a short story. I didn't know if you were
Oh, it's not. Yeah, no, he never used that particular phrase. I
okay.
mean, I thought it was a good. It's very hard to do titles. It turns out that you know Martin Amis, famous English writer that I've read a number of his books, he wrote something called Einstein's Monster. I think it was a
Hmm.
short story though. You're actually allowed to reuse titles in writing, especially between a short story that's fiction and a nonfiction science book. That's okay.
Hmm.
But it is hard to be find a completely novel title with just a few words.
Yeah.
Um, so yes, it was not a phrase used by Einstein. It was just it was reflecting what Einstein and others' thoughts about these objects were, and of course the popular perception that they're nasty things in the universe that devour everything and could imperil us. So it was a reflection of the popular perception of black holes as well.
Gotcha. And let's see. Oh, somebody before this, someone in our Discord chat asked if you could go into a little more depth about the actual research you did related to black holes, like at telescopes and things. Because I know you mentioned that a little bit in the book, but like some of the
Right.
places you went, some of the telescopes you worked with.
Yeah, my research was on a field that you would summarize as talking about the co-evolution of galaxies and black holes. So one of the interesting things that has emerged in the last few decades, and it's covered in the book in the later chapters, is that not only do black holes form at the center of every galaxy that we've looked at, including our own, of course, but that those black holes have very particular properties. Their mass, in particular, is very correlated with the old star mass of a galaxy. So galaxies with not too many old stars in them, like the Milky Way is an example. Most of the stars in the Milky Way are young, but near the center in the bulge, they're old stars. Would be predicted if there was a correlation to have a smallish black hole, and we have 4 million times the mass of the sun. A big galaxy that's almost all old stars, like an elliptical galaxy, actually they have black holes as many as 1,000 times bigger. So my research was partly designed to try and understand that correlation because the black hole in a galaxy is in a tiny, tiny, tiny fraction of the volume. And it's actually a tiny fraction of the total mass of a galaxy, less than 0.1%. So it's not obvious at all why those two things should be so tightly related across decades of mass in the universe and in every galaxy we've looked at. So that drives some of my research. And the second question about the research or revolving around the research is why are most black holes in galaxies dark or hard to detect? So, in other words, a black hole, of course, is dark by definition, but they are the most active emitters of radiation in the universe when they are fueling, when they're gaining energy by accreting matter. And in the center of a galaxy, there's a lot of stuff. There's a lot of gas and dust, and stars are losing mass all the time. So there's plenty for a black hole to eat and therefore be bright. And then it becomes a question, why are 99 or a large percentage of the black holes in the center of galaxies dark, not active? That's again not obvious why that would be the case. So part of my research was answering that question. Those are two big questions that my research, of course, couldn't fully answer either, and they're both not fully answered yet. So maybe a dozen research groups are working on these questions, and they have to do this observationally. You have to essentially gather properties of black holes and their surrounding galaxies across cosmic time and get large samples of tens or hundreds actually of black holes to try and understand statistically what's going on. And so I had to use our kind of frontier facilities. The best tools that I used for quite a while actually were the Magellan telescopes, our 6.5 meter telescopes in Chile, which have great instruments for doing this kind of work. So this research needs what in modern day are pretty big telescopes. Now, of course, there are bigger telescopes than 6.5 meter, but that still counts as a pretty large telescope.
Mm-hmm.
So I did a lot of that research in Chile, which is, a wonderful place to observe.
Yeah. And then you guys involved in the next Chilean telescope, which is very exciting.
That's right. Down in Magellan, we've made 5 mirrors already, so that's almost certainly going to get its first light in probably 4 years, I think.
Yeah, that's exciting. So I think we're going to switch gears a little bit and go more towards the science side, because we have a few people with questions about that.
Mm-hmm.
So one of our viewers, Parzival Fusto, asked, in the book you focused on like every topic of black holes, like as we discussed before, you cover a lot of different things. They were wondering if what you think we would be able to do if we could someday travel to a black hole to like unravel the nature of it. I think maybe what like experiments maybe we could do.
Right. So the nearest black holes are quite far away, hundreds of light years. We know that. And that's expected because the dead star that dies as a black hole is one of the most massive stars, and most stars are not massive. So it's rare stars that die that way, and so we wouldn't expect one to be nearby. So it's, as a practical matter, it's really not going to happen anytime in the foreseeable future, since we can't get out of our solar system. Certainly, with people, we've only got to the moon, so that's 50 years of the space race. So it's pretty slow work. But if we could get to a black hole, a nearby black hole, it's a dead star black hole, we'd want to do physics experiments up close and test general relativity and see if the distortions of space and more particularly maybe time are as predicted by the theory. So, if you were able to get close to a black hole, you could see the physics, which we just understand in general terms from the theory. You could see it up close, and you might find new phenomena, of course. There might be new physical phenomena associated with black holes that the theory doesn't directly predict, or that we just can't see with our current views of black holes because they're far away and we don't see any detail. I mean, in all this work, there's only been one image of a black hole, the event horizon, from a few years ago.
Mm-hmm.
A massive one quite far away. That's the only one. It's just hard work.
Yeah. And feel free, viewers, to ask any questions. By the way, I'm taking some questions from chat and some questions from before. Somebody named Iger Zoom asked, does your book address any theories of black hole interior mechanics? I actually can't remember at the moment.
Not very much, because those theories are not, they're considered frontier and speculative. Because, conventional black hole theory doesn't actually speak to the interior of a black hole very much. There are theories that describe in a spinning black hole how you can have very interesting space-time curves where, in principle, if you could be in that situation, you could travel backwards and forwards in time. They're called time-like curves in general relativity. So it's a phenomenon of general relativity. So yeah, there are some interesting phenomena that result from a spinning black hole, the interior, inside the event horizon. But the theory is not really very predictive about what the situation inside a black hole is. Or even if the singularity is an absolute necessity of black hole theory. It's a general prediction of the theory right from the beginning, that there would be a cusp of density, infinite cusp of density, which is unphysical. So it indicates that black hole theory is not fully mature. So it's really partly that. It's the fact that the black hole theory is still fairly rudimentary. It means we don't have a lot of detailed predictions of what's going on inside.
Mm-hmm. And speaking of, you mentioned the spinning black holes there. Somebody else also had a question, I think a clarifying question from one of the chapters. They asked how the rotation of a black hole affects the energy and the X-ray brightness.
Well, spinning black holes in in situations, they're usually in binary pairs, the ones that we know of course, that's how we detect them because of their visible companion. Um, but generally, spinning black holes um, can be very efficient at accreting material. So they will form, because of angular momentum, they'll typically form a disk of material around them that's quite hot, maybe 100,000 Kelvin. And that material can, along the circumference and the inner radius, can fall into the black hole and get accelerated. So spinning black holes with accretion disks around them, which we think is a general configuration, are extremely bright in X-rays because the disk itself, the accretion disk itself, is hot enough to glow in hard ultraviolet radiation or soft X-rays. And then the region of acceleration of plasma near the black hole uh, is a place where high energy particles are emitting X-rays, gamma rays, the full high energy spectrum. So yes, spinning black holes are producers of enormous amounts of high energy radiation.
Gotcha. And then we have a couple questions from people that asked before this. So if you were to fall into a black hole before the spaghettification gets you, the universe would see you get quickly redshifted to infinity. Does that mean you would get vaporized by light that's blue shifted to infinity?
No, it's a perspective thing with relativity. If you were viewing someone falling into a black hole from nearby but a safe distance, um, you would see as the light, to use an analogy that's sort of anthropomorphizing it, as the light struggled to escape the gravity potential, it loses energy, and that's the redshift. It's gravitational redshift. And at the event horizon, that gravitational redshift becomes infinite. And that's the sort of logical physics explanation for why nothing can get out of a black hole, because at the event horizon, you're defining a region of density interior to that, where the escape velocity is the speed of light, and where radiation is infinitely redshifted or degraded in energy, and therefore no energy gets out. So that's the way it happens in physics terms. And so as you fell in, the radiation, the light reflecting off you that let someone see you falling in, would suffer that. It would suffer that extreme redshift. And the closer you got to the event horizon, the more redshifted it would be. Now, redshifting is reducing energy as well as shifting the wavelength beyond the visible spectrum. So at some point, even if there was light shining on you as you fell in, the person watching would not see you anymore. You'd fade to black because whatever energy, whatever reflected radiation was coming off you was being shifted to infrared or even radio wavelengths, and eventually no radiation coming off you. So that's what a viewer would see. Now, to your perspective, intriguingly, you just fall into the black hole. And if you were looking at yourself, if you could look at yourself, you wouldn't see anything peculiar, except of course you being stretched by the gravity, and that's another story.
Mm-hmm. Let's see. I see a couple questions in the chat that are a little off topic kind of things. So I might do a few others and then maybe we'll get back to those. But here's another one that somebody discorded me. So here we go. Some supermassive black holes that have been discovered are young and massive enough that they would need to have been accreting material at a super Eddington rate since the universe was born to be so massive. Are there any leading theories for how these black holes form?
Right. That's an interesting topic. That's subject of a lot of research. I worked a little bit on that some years ago. One of my colleagues here at Stewart, Zhao Fan, has done a lot of work on this, as he's one of the world's experts on early massive black holes and the challenges they pose to theory. So basically, we've now found quasars, or active galaxies that are powered by black holes at very high redshift, at times about a half a billion or 700 million years after the Big Bang. It's almost, and yet these black holes, based on the luminosity of the quasars that we see, are maybe a billion solar masses. And it's been an issue, it's been a known issue for a decade or more, that it's quite challenging to grow a black hole to a billion times the mass of the sun in less than a billion years. That's really hard to do.
Mm-hmm.
Later in the universe, when the universe thins out and expands and galaxy interactions diminish and the amount of gas available to fuel a black hole diminishes, black holes grow at a much more sedate rate. Now, in the early universe, they can grow quicker because galaxies are merging and assembling, and so the black holes at their centers will merge and grow by addition. And there's a lot of gas around because not all of it's formed stars. So you can indeed grow black holes quite quickly. But some of these black holes are so big and they're seen so close to the Big Bang that they've been seen as a challenge to theory, as a fundamental challenge to the fact that they're black holes in the first place, because if you can't figure out a reasonable way to build one that big, then maybe the interpretation is wrong. It's not a black hole. Nothing has got to that point of refuting the idea that these are black holes in the first place, because it turns out that, in the early universe, when galaxy building is a big project going on in a much hotter, denser universe, you can grow black holes very quickly. That's super Eddington. Super Eddington is just the technical term for a black hole that's growing at a faster rate than you would expect just from gas falling spherically onto a central object. So you can grow black holes at a fast rate, perhaps fast enough that it's not a problem to see a massive black hole there. But to avoid that problem, another possibility is, what are the seed black holes? If you start with very small seed black holes that are only the size of massive stars, for example, then to grow through the decades from 100 times the mass of the sun to 1,000 to 10,000 to 100,000 to a million and so on, it does take a while. If the seed black holes, the very first nuclei black holes in the very first generation of galaxies, are more massive than we originally thought, then you get a head start. You get a big head start on building black holes. And there are ideas now that the first generation of seed black holes may have been quite big, hundreds of solar masses rather than tens of solar masses, or maybe even 1,000 times the mass of the sun. And that sort of jump starts the process of black hole growth. And I think at that level, you no longer have a fundamental problem explaining these big black holes. They do, however, have to be rare. They represent a rare pathway in black hole evolution in galaxies. Most galaxies will just not go through a history that would let them grow a black hole that big that quickly. So it has to be a rare object. And so far that's okay too, because the big black holes that have been found close to the Big Bang are very rare. There's literally just a handful of them. Mm-hmm. So I think the theory is still viable, but it's a very interesting type of observation.
Yeah, I heard about that, and it seemed very interesting. A new topic to research in black holes physics. All right, so we've got another question from the chat. Did a supermassive black hole influence the evolution of life on Earth?
It doesn't seem so. The galaxy that we live in has a modest-sized black hole. It's about just under 4 million times the mass of the sun. That's pretty small for galaxies. So the galaxy black holes go up to 1,000 times bigger, so making ours pretty small. And if you look, it's 28 or 29,000 light years away. So if you look at that, as far away as we are from the center of our galaxy, that black hole at no point in its history has ever, had much influence on us gravitationally. It's just too far away. However, the slight caveat on that is that our galaxy black hole is pretty quiet now. It's quiescent or dark. It's not actively accreting. It's not that bright in any radiation. And so the question is, well, if it was in an active phase, what would that do? If it was in an active phase, it could be thousands or millions even of times brighter than it is now in terms of non-thermal radiation. And at that point, in principle, the center of our galaxy, black hole, would be as bright as the brightest star in the sky, and brighter than any star in the night sky. Not as bright as the sun, but a substantially bright object, and a lot of high energy radiation.
Mm-hmm.
And so there's a speculation that if there had been an active phase of our center galaxy's black hole, it might have influenced life on Earth that way. However, in practice, it doesn't work, because we are in a disk-like galaxy, and the path between us and the center is just jammed with material. It's jammed with all the gas and dust between all the stars and the disk of our galaxy. And that material, that gas and dust across almost 30,000 light years of space, is very good at absorbing, scattering, reflecting, and quenching the light from the central object. So basically, given the geometry of our galaxy, even if our central black hole went through a quasar phase, for example, as has been speculated, I don't think it would have affected anything on Earth.
Gotcha. And this is a question from me again, but I was wondering, we talked a little bit about, with super Eddington black holes and some other things about like future research into black holes and how it's still continuing, of course. If you, barring any like actual, this is a very theoretical question, but like barring any actual like human ability to get to places and technology limits and stuff like that, what would be like the experiment you would do on a black hole, or like with a black hole? Like what would be something that you would really want to do or find out?
Yeah, I mean, I would actually sort of come back to this information paradox. I would come back to the problem or the issue in physics of what happens at the event horizon. What is the mechanism that makes Hawking radiation? Does Hawking radiation exist? I mean, it's very unlikely it could be detected astronomically, because it's so feeble. The temperature is a tiny, tiny fraction of a degree, maybe a billionth of a degree. There's no way we can detect such a tiny temperature. So that would be a very important experiment, to detect Hawking radiation, to understand what's going on at the event horizon, that exotic physics. So that would be the stuff inside the black hole. That's just so hypothetical, and you wouldn't survive going in unless it was a massive black hole. You could survive into a massive one, but there's no massive ones near enough, with 30,000 light years to the nearest massive one. So I think understanding the event horizon physics would be very interesting experiment to do, if you could do that kind of experiment.
Somebody asked in the chat, they are a biologist, and to them it seems like, this is going back to the if life on Earth was influenced by a massive black hole. But they asked, it seems to them that the evolution of life on Earth occurred over a very short period of time compared with the times involved in these galactic processes. Do you believe this is correct, and that life is a very short period in the universal timer?
Well, I think life's been on this planet for almost 4 billion years, and that's quite a long time. That's a third of the age of the universe. So life has been around for a long time. And there have been astronomical influences and impacts on life. We know that. There's a lot of debate, of course, about mass extinctions. And only, now it's not even clear that the KT boundary at 65 million years ago was caused unequivocally and solely by an impact. It may have been a geological devastating effect too. But so we know the impacts affect the history of life on Earth. Also, the sun at its position out in the disk of the galaxy goes in and out of the plane of the galaxy, just a natural oscillatory motion for the period of 30 million years or so. And there's speculation that when the sun and the solar system and the Earth too pass through the plane of the galaxy and through denser regions of stars and gas, that has effects, maybe triggering the comet cloud to send a lot of comets into the inner solar system and more impacts and so on, or higher radiation environment because there's supernovae nearby. So yeah, there are astrophysical potential effects on life on Earth over the time scale of tens or hundreds of millions of years. None of them are really implicated with black holes, though. except possibly if there was a massive star that died near um, the sun, by which I mean 10 to 20 light years away, that supernova could have had a dramatic effect on life on Earth. And after the supernova, you'd have left behind a black hole, which you might not know was there. If it was a single star black hole, you might not detect it. And the supernova went off so long ago that you wouldn't see the debris left over from it too. However, it could have had an effect on life on Earth. So some people have even speculated about that kind of thing too. So that's probably the only example of a black hole effect on life on Earth that's hypothesized, where we don't really have evidence for it, but it's not unreasonable that it could have happened over the long span of life's history on this planet.
Mm-hmm. And going a little bit back to research and things on black holes, I was wondering if during your research, if you ever used any of those huge supercomputer-esque simulation softwares to test theories or things, or if that was sort of a different sect of research.
It's a very specialized field, so simulation astrophysics is very big. It's very important now as computers have become more powerful. It's become a significant part of the subject because the astrophysics is complex, and you can't always do it simply with equations. Simulating the physics is very powerful in complex situations. And now the computers are so powerful that you don't need a supercomputer. You actually need just a very powerful desktop computer with maybe 64 parallel processors, which is as good as a supercomputer 20 years used to be. Mm-hmm. So it's a very important part of the subject, an important part of understanding massive black holes or how they form in galaxies, the subject we were talking about. It's an important part of understanding the astrophysics of what's going on near a black hole, the particle acceleration and the intense radiation that comes from black holes. But it's a highly specialized field of astrophysics, numerical astrophysics. It involves people who are expert programmers and know how to parallel processing has to be used. And then they also know a lot of astrophysics too. So they tend to be sort of theoretically inclined astrophysicists who have a strong talent for programming. And that's a niche that I would have had to have been trained in, many years ago. At this point, that field has become its own thing, and you have to be an expert in that field. So you'd have to do your graduate work in that field and be a postdoc, and then follow that for your career. Mm-hmm. It's not really a crossover thing.
Exactly. And actually, speaking of going to school for astronomy and computer science and things, somebody earlier asked, this is a little off topic, but we're getting towards the end, but they asked if a math major could go into astronomy for a PhD, if they did a math major for undergrad.
It's possible, and the math is very important, and astrophysics, has a lot of mathematical methods that are used. So the math is a great advantage in studying astrophysics. The only problem with a math major going straight into graduate work in astrophysics is you'd have a lot of deficiencies in physics, because most people who do a PhD in astronomy or astrophysics have done an undergraduate degree in physics and maybe a double major in physics and astronomy or physics and math. So there are definitely math and physics double majors, but the physics is an important part. So it feels like to make that transition, you'd have to do a sort of quasi-master's program that sort of booted you up to sort of senior and almost graduate level physics before you could segue into a PhD program. So it is quite challenging for that reason. But math does give you a great advantage going in over other fields, for example, probably bigger advantage than, say, chemistry would.
Mm-hmm. And I think we're getting towards the end. I know it's about 10:50 now. Well, for me, 11:50 for you. So I think I'll wrap it up with just one more question. So this is your 8th book, as you said, and before the chat, we were joking a little bit about you trying to figure out what to write for your 9th. What are some things, if anything, that have been bouncing around in your head to be the next book?
Yeah, I mean, I have sort of tossed up tossed around a few ideas. I think I've done enough on cosmology now that I don't really feel like I need to revisit that necessarily. Um, but my first popular book was The Living Cosmos. That was about astrobiology, and that was a decade ago. Um, and a decade in that field is an enormous amount of progress, and especially on the exoplanet part. So I think exoplanets are a topic that I would like to visit again because it's a field that's moving so fast, and it's very exciting, and it relates to this search for life in the universe, which everyone cares about. So that's sort of top of my list, I think, for our next book. It may be a slightly crowded field. There have been exoplanet books in the last few years, and when you pitch a book to a publisher, and I've had 4 consecutive books with Norton. I like that publisher, but it has to fit their marketing and their strategy for science books, and you can't go into too crowded a field. Um, so there's a sweet spot between writing something that's novel and interesting because people haven't read about it before, and being in a field that's so hot that even writing at a popular level, there's too many competing titles, and then it's seen as being too crowded because the publisher wants you to sell books. So it is a business after all.
Yes. An exoplanet book would be really cool, though. I've always loved exoplanets. We've talked about it a few times. We've done dedicated exoplanet streams like once or twice on with Michael on Wednesdays. But somebody actually asked in the chat really quick, are you planning a new edition of your astrobiology text?
The Living Cosmos, that book was written for Random House originally 10 years ago, and they actually sold it to books get sold. The rights to books get sold all the time, actually. It got sold to Cambridge University Press, so the copyright is held in the paperback version, which I did update a few years ago, but it's now 6 years ago. Is owned by Cambridge University Press, and they have a pretty nice, decent price on it. So it'll be up to them whether there will be a second edition of that book. In truth, for that book, I would wait till life is actually found somewhere else, and then that would be a wonderful second edition to talk about how life actually was found. Because in that book, I just play out all these possibilities for how you might find life. Mm-hmm. And of course, an exoplanet book is treading the same ground, because we might well find life first by looking at the atmospheres of exoplanets in the nearby universe. That could happen within 5 years, and so that's another book that is in danger of being out of date if it just misses the first discovery of life on an exoplanet. So I'm hoping for progress in that field, but I'm also hoping not to finish a book and just after it gets published have to really change it a lot.
Yeah. Especially if it happens like right after you send it to the publisher or something, and then it's like a few days later, it's like, oh, and we found life. Like,
yeah, I mean, it's a double-edged sword. It makes enormous attention on that field, so people want to know everything about exoplanets. Mm-hmm. But the book, so it'll actually bring attention to a book on exoplanets, but the exoplanet book will not tell them the single thing they wanted to know most, which
exactly.
is the discovery itself.
Yeah. All right, and one more thing to leave the stream on before we close out. So we're going to be doing more book reading for the next couple months, and we voted, and the next book we're doing is Dreams of Other Worlds, which is your book on unmanned space exploration. So did you want to give us like a little preview of what that book's about and stuff for those who might be joining us next week?
Oh yeah, that's the one. It's the one I co-wrote with Holly Henry, so that's one of my co-authored books. Yeah, that was a book that I enjoyed writing. It's first since I wrote a textbook with Bill Hartman, first time I co-authored a book. Yeah, we just tried to pick iconic space missions in the last 50 years that had changed our way of thinking about different parts of the universe, and so that includes some planetary missions. It includes some of the big astrophysics missions. Hubble Space Telescope, of course, will always feature in any list like that. And so, yeah, that was a fun book to pick, sort of highlight missions that really were so visionary, so well designed, so well executed. They single-handedly, each one, transformed our view of the universe in some way, and went into the popular consciousness as Hubble did through its images and so on. So that was a book that I wrote a few years ago, but I enjoyed the process of writing it actually, and of course picking the missions themselves. What do you pick and what do you leave out?
Mm-hmm. Great. Well, I think that's about it. So really quick before we go, first of all, thank you so much, Chris, for joining us. This was so much fun to talk about your book and everything, different from our regular Q&As with you.
Right. Well, thanks. I enjoyed it too, and thanks to all of you out there for those questions. Good questions too, and look
Yeah.
forward to the conversation in the future.
Yeah. So for viewers, just a couple, closing out notes. First of all, thank you, Zoom and Ox Bowman, for following us. If anyone else is here and hasn't followed yet, please do. You'll get notifications for when we go live in the future. We do regular streams every Monday. I read another chapter of one of Chris's books. Like I said, we're doing, unmanned space exploration. Oh, thank you for that follow, Ivan Choamb. I'm so bad with names on here, but I hope I pronounced that okay. But yeah, make sure to follow us. If you can, we are Twitch affiliates, so if you can subscribe, that's a super great way to help out the channel. If not, that's totally okay as well. But this week we will be back on Wednesday. Me and Michael will be doing astronomy news, and then on Friday we will have amateur astronomy with Matthew. So I hope you guys can join us. Thank you guys so much for being here, and I hope you all have a happy Monday.
Okay, thanks. Bye. Goodbye, everyone. Bye, Vic.
Bye.